So in the last two classes, we have seen the preliminaries for this course, preliminaries on operators and Hilbert spaces. Now we will make the first definition. Okay? The definition we are going to study the C-star algebras, basic definitions and consequences of C-star algebra. So before that, we want to define what is called a Banach algebra. We'll define a Banach algebra, then we will impose a star structure, and there will be a C-star condition. So this is the definition. A is a Banach algebra. Let me not write formally. I'll just tell you what are all the structures in that Banach algebra. First, it's a Banach space. So it's a non-linear space, which is also complete, a Banach space. That is non-linear space, which is complete also. Okay. Then it's also an algebra. So Banach space, it's a vector space, so it has addition, scalar multiplication, and it's an algebra, so it has multiplication. So the addition is commutative, the multiplication need not be commutative. So it's an algebra. Algebra means which is a ring plus vector space. A ring, so the multiplication is associative multiplication, and it's a ring plus vector space, so these two operations should be compatible. So it is just the distributive law. There should be distributive law connecting this multiplication and addition. So that's what an algebra is. So it's an algebra and it's a Banach space. And we need this algebraic operation. This is multiplication. So when you have a Banach space, you have a norm. So addition, scalar multiplication, they are all continuous. If you have a Hilbert space, then indeed the norm is also continuous. Okay, if x going to norm x, this function is also continuous. So all those functions are continuous. So in an algebra, we would like the multiplication to be continuous. So for that, it satisfies the following. Satisfies norm of xy is less than or equal to norm x, okay, for all x. So a Banach algebra is a Banach space, and it's also an algebra, and the multiplication satisfies this inequality. So as you can see, when you have this inequality, it means the multiplication is continuous. Okay. Okay, so the consequence. So first remark is x, y, and a cross a going to a, which is just xy going to xy, is continuous. Okay. So this is clear. If xy goes to some, then xn goes to x, yn goes to y, then xn yn minus xy will be equal to xn less than or equal to xn yn minus xn y plus xn y minus xy, which is less than or equal to norm xn times, maybe you put a supremum here, less than or equal to supremum over n. This, since it's a convergent sequence, this should be finite, and xn minus x plus norm y times norm, here yn minus y, from y times xn minus x. So it will all go to, that will go to 0, so it converges. So yeah, now, so multiplication is continuous. And we can say something more. If you have a Banach space, you can actually embed that Banach space as operators. No, if you have a Banach algebra, you can embed that Banach algebra as operators and a Banach space, where the Banach space itself is A. Okay? So this is another remark. Or 2, if you have a x in A, you define Lx is an operator from A to A. This is a Banach space on its own. So you can define an operator. This is L is for left, and it's left multiplication. So Lx acting on y is just xy. Similarly, you can define on the right. The calculation is same, but this will be a representation that will be what is called an anti-representation. It's not the product will be flipped, reversed. So now you can see that this is continuous. So we know that Lx of y, norm of this, I mean, this is the operator now, okay, which is Lx of y equal to norm xy. No, Lx, this is not operator, this is C star norm, Lx of y in C star norm. This is norm xy is less than or equal to norm x times norm. So this implies the operator norm of Lx is less than or equal to norm x, right? By the definition of operator norm. And you have to say that this is equal to that. So for that, you have to say that the supremum exists. So if you assume the Banach, I mean, okay, I forgot to say, all our Banach algebra will be unit. There will be unit. Okay, let's not complicate. Actually, we can unitize it and let's not worry about it. For our purpose, all our Banach algebra will be unit. Okay, so let A is a unital Banach algebra. That is, there exists an identity element. Okay? That is, there exists one in A, such that 1x equal to x1 equal to x. Okay? There is an identity. So Lx acting on 1 is going to be x norm x. Okay? So this is how you always calculate, I mean, usually calculate, unless you approximate it by a supremum or something. So this implies operator norm of Lx is equal to norm x. So this says that the x going to Lx is an isometric embedding of A into B of A, whatever. We say B of A is by all the bounded operators on A. B of A. I mean, some people say L of A, which is linear operator, but I want to say bounded linear operator, so B of A. In fact, Lx Ly is equal to Lxy, and Lx inverse I mean, Lx inverse means not the inverse of the, I mean, it's inside as operators, the Lx inverse. Lx is is operator from A to A. I mean, not inverse of this. If it is Lx inverse, is L of x. You can just verify this. Okay. I mean, it satisfies the property of the inverse, and you can verify. So similarly, you can define x going to, I mean, you can go to x going to y going to xy inverse. This will give a representation of, I mean, you can embed this algebra A into B of A. Similarly, I mean, you need y inverse because you want to respect the product. If you have xy, then xy will go to, I mean, you can call this Rx. Okay. Then if you have only y here, then Rx, Ry will be R of yx. Because it's right multiplication. So you want to get the representation, so you put the inverse. Okay. Huh? You just write down this, I mean, inverse is something, if you have an operator T, the inverse is whatever Ts equal to 1. The identity operator is there, and this will satisfy this. Anything is, when is inversible, sorry. When it is inversible. I'm not saying, sorry. When X is inversible. Yeah, sure. Norm of 1 is 1, correct, yeah. Correct, you are right, sorry. Yeah, which is need not be true in the Banach algebra. I mean, yeah, which is not true in the Banach algebra. So we have to assume norm of 1 is 1, which is true in C-star algebra, sorry, yeah. This is in the general Banach algebra setting, it's not, yeah, it's not true, yeah, correct. So norm of 1 is equal to 1. So we are assuming that also. Okay. So let's see some example. I'm sure all of you have seen this example. So first, I mean, the most general example we are going to consider is B of H. Okay? And this is a Banach algebra, you know that. I mean, operator norm satisfies that Banach inequality. And any closed algebra or any closed subalgebra of B of H. You can take any closed subalgebra of B of H. And this is another example, C of X, continuous function, X is compact. I mean, Hausdorff, compact Hausdorff. So then C of X, this is a Banach algebra. It will be C-star algebra when we define that. So with, I mean, this is because, I mean, I don't have to verify. Supremum of f of x, g of x is less than or equal to individual supremum. You first, I mean, you do this, first g of x is less than or equal to individual, the supremum of mod f of x times supremum of mod g of x. Then this is just a number, then you take the supremum here and you will get it. Okay. So, and third example, we will not consider this, but I'm just saying, if you take any set S, then B of S, all bounded functions, all F from S to C. Usually we will deal with only our algebra or vector spaces are over complex numbers. Okay? We will not deal with real field, okay? All complex field. But I think I have said it in the starting. Our Hilbert space, everything is over C. All vector spaces are over C, unless it's being explicitly stated. So this is, I mean, with respect to point-wise product, this is also a Banach algebra. You can see. Okay, I mean, it's clear, right? The same proof will work. C of x. There's no difference. It is just, I mean, C of x sits inside B of x. C of x is contained in B of x. For that. Okay? It's the same thing. Okay? Then the fourth one is if x is a measure space, then you can talk about L infinity of x, which is all those essentially bounded functions, all functions from x to c, such that there exists a set E contained in X such that mu of E equals 0 and F is bounded. F restricted to E complement is bounded. Okay. Then you can define norm F infinity. I mean, here also we use the F infinity norm only. I mean, these are all contained in that. I mean, for continuous function, I mean, this is not correct. You have to take equivalence classes. You have to identify function up to equivalence. I mean, up to measure 0. So I'm not saying all these things. Okay, it will be. I mean, I mean, by abusing, we just can't talk about single function or something. Actually, we have to consider equivalence class. Okay? So norm F infinity is infimum of all those k, such that there exists. I mean, there exists this all those. There exists a set of measure 0, and outside that it is bounded by k. You have to take the infimum of this. Have you done these things? L infinity is a Banach space. All those things. Jana 1. So maybe we can go through it as a presentation or something if needed. So actually this infimum norm is actually a supremum. You will get a set E. Outside that it is actually, it can be written as a supremum so that you can verify all this. Okay? You can verify that it's a Banach algebra. If needed, I mean, we will not consider this. We will be basically dealing with C of x for our purpose. Actually, we will be considering it in the behind the scene, this L infinity. It will be, I mean, when we do the spectral theorem, it will be there. So this is, I mean, whatever we have seen till now, they are all not just Banach algebra, they are also C-star algebra. Okay? This L infinity is something more. It will be what is called a phenomenon. So when we need, we will come to that. So I mean, I hope I don't have to do why this is Banach algebra and all that. I hope you can do that. Okay. So, okay. So these are examples and non-example. Non-example means this is the example of Banach algebra, but it's not a C-star algebra. I haven't defined what is C-star algebra. When I come to that, I will tell you. So this is again X mu is a measure space. I mean, this is an example, but it's a non-example. When I define C-star algebra, it's not a C-star algebra. Measure space. Then you can talk about L on X mu. . And here you define F star G. equal to integral over x f of s minus t d f of s minus t f of g at s equal to g of s dt. I hope I have written it correctly. Okay. This is the convolution. With respect to this convolution will satisfy, I mean, you have to verify all that. This convolution will satisfy the Banach that inequality, Banach inequality. And this will be a Banach algebra. And this will not be a C-star algebra. If needed, we'll see a proof of this. This will not be a C-star algebra. When I define C-star algebra, we'll see this. And you can have more definition of Banach algebra, which are not C-star algebra. For example, this is a Banach algebra. You can take the Rn, you can have any norm on this. But then only with respect to the L2 norm, Hilbert space norm, the MNC will be a Banach sister algebra. With respect to other norms, it will not be a sister algebra. And you can define the adjoint through the same, I mean, you can define the star using the same adjoint operation. Anyway, I will come to that. This is just an example of a Banach algebra. We will not be using these things. This is just an example. Okay. Say it again. What is vector space X? That should be a group, sorry. Group, and you have a nice measure. Yeah, it should be I think it should be okay, let's take mu as a Haar measure. I mean, let's take R and then some Lebesgue measure. Okay. Lambda, Lebesgue measure. Just an example you need. Or you take small L2 and you can define the same convolution. Okay, it will work. So in general, with respect to, I don't think you can define, I think you can define it for any mu. I don't remember. Okay. That's fine. Any locally compact with Haar measure or any measure you can define. Yeah. So with what happens when it's not a Haar measure? What is the problem? If it's not a Haar measure, no, I think it's still a Banach algebra. With respect to any mu, you can define it, call it, it will define a Banach algebra. I'm not sure. What I'm asking is, if you have, this convolution, no, you can define convolution for any measure, right? Yeah, this F star G. It will be a, yeah, but why is it needed? I'm not sure. Say it again. Correct, yeah. No, there is only one condition, no? That Banach, that equal to. Complete shouldn't be a problem. I mean, complete is just a vector space. No? It is complete. It has nothing to do with that. So you define the convolution, and the convolution has to satisfy that inequality. That's all the Banach algebra. Okay. So let's call it. Let's take any group, any locally compact group, and take the Haar measure or real line with lambda, or L2 small L2 with counting measure. Okay, that will work. Okay. Okay. Well, we will be working with basically with C star. So we will be basically dealing with B of closed subalgebras of B of H, and indeed we will be dealing with C of X, which will be the commutative C star algebra. We will be basically dealing with this, and maybe L infinity behind the scene. Okay? Or if you are interested, we can do other things. I mean, that's later. After proving a spectral theorem, we can do. Convolution is? Okay. Okay. So let's prove the first lemma. Is something we may be using it again and again. So A is a Banach algebra, unital Banach algebra. We will always use unital Banach algebra. So that's why we talk about inverse and other things. unital Banach algebra. X is in A, and we have this condition 1 minus x is less than 1. X is at a distance from the identity, I mean at a distance less than 1 from the identity, then X is invertible. And X inverse, you can write it and equal to 0 to infinity 1 minus X power. Proof. So this is a Banach space. So any absolutely convergent sequence, that is if A is a Banach space. So if summation mod yn, norm yn less than infinity implies summation yn converges. Okay. This is true in any Banach space. Okay. I mean, this is less than infinity is equivalent to saying summation n equal to k equal to m to n yn. This goes to 0, right? Okay. And that implies summation yn yk k equal to n to m. This norm will be less than or equal to this. This goes to 0. Okay. Right? I mean, I'm just saying that any absolutely convergent sequence will converge in a Banach space, which we know for real line. It's true in any Banach space. If absolutely convergent means this is less than infinity, which is equivalent to saying m equal to n, this goes to 0. Okay? And this is less than or equal to this. This should go to 0. And that's precisely what it means by this. This is a Cauchy sequence. So that converges. Okay. Sorry, this is Cauchy. Sorry. This just implies this goes to 0. This implies this is Cauchy sequence, n equal to 1 to n, yn. This Sn is Cauchy. This is Cauchy. So converges. Okay. Actually, the other way is also true, but we need to work for it. Other way is, if every absolutely convergent sequence also converges, then it's actually a Banach. Then it is complete. It's a criterion for completeness. Okay? I mean, if you have, and I mean, we may not use it when we don't have, we will not need that. For example, I think if you want to prove the quotient space is complete with respect to quotient norm, I think one will use this. I mean, the converse. Converse is if every absolutely convergent sequence converges, then it's a Banach. So now all we have to do that this to prove that we want to first say that this is convergent. Okay? So since summation n equal to 0 to infinity norm 1 minus x n, of course this is less than or equal to summation n. I mean, you can take the product out with 1 minus x power n, and this is less than 1. So this is less than infinity. So this is geometric series. So this is less than infinity. It's just a geometric series. This is less than 1. So this is less than infinity. Okay. So this implies summation n equal to 0 to infinity 1 minus x power n converges. Now we have to verify this is actually the inverse. Okay. Let this is equal to some s. So let Sn equal to summation n equal to 1 to n equal to 0 to n 1 minus x power n. Okay. Then Sn into 1 minus x, you multiply 1 minus x, which is equal to Sn plus 1. I mean, you multiply by 1 minus x. So if you multiply by n, you will get, I mean, if you multiply Sn into 1 minus x equal to Sn plus 1. I mean, it will start with, I mean, the same sequence will start with 1 minus x. Okay? I mean, here 1 minus, I mean, we have to assume that 1 minus x power 0 is 1 identity. Assume. I mean, standard 1 minus x power 0 for any operator is 1. So this is equal to this, which is also same as 1 minus x into Sn. Now we just cancel the terms. So now let n goes to infinity. This implies s into, I mean, and Sn goes to s, let us say. Sn goes to s. Then s into, since the sequence converges, s into 1 minus x is equal to s minus. So which implies, I mean, which is also equal to 1 minus x into s. So if we cancel the term, it will imply sx equal to 1 equal to xs. Okay. So s is equal to x inverse. That's all. So the corollary to this is, so let's make a definition. G of A is also all invertible element. Then corollary is G of A contained in A is open and H going to X inverse is a homeomorphism. Proof. So this lemma implies B of 1. I mean, this 1 is in A. This one is number. Okay. This is some number. Okay. This is contained in A, G of A. Okay. This one is A. I mean, this is open ball around A with radius 1. Okay. The open ball around 1 with radius 1. Okay. This is in real number. I'm just using the same one. Okay. So this implies 1 is an interior point. Also, you want to say it's a point of continuity for inverse, I want to say. Okay. So suppose you have a sequence Xn contained in all invertible elements and Xn converges to 1. Okay. Then we want to say that Xn inverse also converges to 1. Okay. So, and we know that after, I mean, when it is 1 is, I mean, we assume that it's in a open, after some time it will be in an open ball. So without loss of generality, we assume that it's in an open ball of radius 1. So, I mean, then only we can write this. So Xn inverse will look like 1 minus Xn power n. Okay. Right? Right now. Huh? Ah, there is a n. Okay. K. Sorry. Yeah. Hmm? Now I want to say this, I want to consider this now. Xn inverse minus 1. Okay. So the first term is 1. So Xn inverse minus 1, the first term will go away. So this is just K equal to 1 to infinity 1 minus Xn power K. Okay. And you have the norm here, which is less than or equal to, of course, K equal to 1 to infinity norm 1 minus Xn power k after using the Banach inequality. You take the product out. Okay. And this is equal to, of course, norm. This is again a geometric series. Norm 1 minus xn by 1 by 1 minus norm 1 minus, which goes to 0. So this is a point of, one is a point of continuity. And I mean, one is an interior point and one is a point of continuity. Now you can use this Lx. For example, Lx is a continuous function. Continuous. I mean, it's a continuous linear map on continuous on A. Okay? And in particular on G of A also. Let x be invertible. Let x is in G of A. X is invertible. Okay? Then if xn converges to x, okay, then Lx inverse of xn, okay, will converge to 1. Okay? So this implies Lx inverse xn inverse will converge to 1 by what we have done. Okay, it's one is a continuous. So this implies xn inverse, I mean, which is just x, which is just x inverse xn inverse. So which is just xn inverse x will converge to 1. And you can apply Rx now, which is also continuous. This implies xn x inverse xn. By applying Rx, I mean, maybe I'll do it. This implies Rx of xn inverse x will converge to 1. Okay. Right? Rx of, no, which converges to, sorry, x. So which is just Rx inverse, sorry, Rx inverse. Yeah. Will converge to Rx inverse, yeah, which is Rx inverse is, Rx will give inverse will give, inverse, it will give the inverse. So it converges, so that's right. So this will be xn will converge here. You can do this, or you can use this inequality directly, this kind of inequality, right? I mean, let me try. Well, you can use the continuity of Lx to get Lx and Rx to get it, or you can write xn minus x, because xn, you'll write the algebraic identity and it will be clear, which is equal to, I want to take x out, right? So xn minus, I want to take x out. So x minus xn. Into 1 minus xn, x minus xn, which will be here will be x inverse, I think. So what is this? This is equal to x minus x plus xn, which is equal to xn. Yeah, you want to prove xn converges to this. I mean, so now, I mean, this is another way I'm just trying. So now this will be, you can, when you have it, I mean, if you want to prove the openness, everything without using that, I mean, this also proves that x is an interior point also. I forgot to say that. Lx is an open map. It's invertible, and it's a, I mean, it's a linear map, which is continuous, and it's invertible. Inverse is Lx inverse, which is also continuous. So it's an open map. So it will take open sets to open sets. So one is an interior point means x is also interior. Okay. Or you can use this kind of, write these kind of things. And in some neighborhood around 1, this will be invertible. And that will prove that if xn's are invertible, I mean, that will, you just take y here. Is equal to y. Okay. That will prove, I mean, that will prove that y is invertible. You can prove that y is, I mean, in the proper neighborhood around this. For example, you can take the neighborhood to be if x minus y is less than or equal to 1 by norm of x inverse. Okay. then this guy will have an arm less than 1. So this will be invertible, right? So you can use that to prove that that is an interior point. I mean, this is x is also an interior point for any x, and you can use the same inequality somehow try. I mean, you can prove that actually this is continuous also. The inverse is continuous. I mean, you have to you have to expand this as geometric series like that, and you will get an. I mean, you have to do the same thing, but you can write it like this. It's just another way of doing without invoking the Lx and Rx. Okay, so we know that this is open. All invertible elements are open, and the inverse map is a homeomorphism. It's a continuous map. I mean, we proved that x going to x inverse is homeomorphism, and similar. It clearly, it's the same map. The inverse is itself. Okay. So now we want to define what is called a spectrum. We do this to define spectrum. So if x is an element of A, the definition is same as for operators. Sigma of x equal to all those lambda in C such that x minus lambda is not invertible. Okay. What is the spectrum? Okay. The spectrum of x for any x in any C star algebra, you can define the spectrum to be like. Then the immediate proposition from what we have done already is sigma x is compact. Compact subset of C. Maybe I'll write a lemma and then I'll come to this. Lemma. I mean, this is a corollary to that. Forgot to say. This is also corollary. If mod lambda is greater than x is in A and mod lambda is greater than norm x, strictly greater than norm x, then x minus lambda is in G of A and x minus lambda inverse is equal to minus summation n equal to 0 to infinity x power n by lambda power n plus. Proof is direct. So norm x by lambda is less than 1. This implies 1 minus x by lambda is invertible. Right? Okay. And 1 x minus lambda inverse. I mean, I want to show this is inverse, but formally write it. Okay. I mean, this inverse is nothing but you can take the minus sign out and it will be lambda x inverse equal to 1 by lambda into 1 minus x by lambda. Okay. Now it makes sense. Once I write this, I mean, here it doesn't make sense, but once I write like this, it makes sense. Okay. This is its inverse. Okay. Now this is equal to minus 1 by lambda into summation n equal to 0 to infinity x power n by lambda power. So when mod lambda is greater than norm x, x minus lambda is invertible, and the inverse is given by this. Now let's prove the proposition that sigma x is compact. So let me write it again. Proposition sigma x contained in C is compact. So C is Euclidean space, so we have to prove only it's closed and bounded. So, so we know that if lambda, mod lambda is greater than norm A, norm X, then X minus lambda is in sigma X complement, which we call it as rho X. Okay, when rho X is sigma X complement, that's the definition. Okay, this is called resolvent. Rho X equal to sigma X complement. This is what is called resolvent. You must have seen this in linear algebra. Complement of spectrum is called resolvent. Okay, so if lambda is greater than norm X, then this is in the. So this implies if lambda is in sigma of X, then mod lambda is less than or equal to norm X. So sigma X is bounded. And we have to show it's closed. So it's enough we prove rho X is open. The map lambda going to lambda in C going to X minus lambda in A is of course continuous. Okay, so lambda going to X minus lambda inverse in A is continuous. No, we don't need that, sorry. Is continuous. So let's call it some F or something. Okay, then F inverse of G of A equal to rho of X, right? If this map is continuous, I mean, it's just you're attaching a scalar to any X. Lambda n goes to lambda, so this will go to, that's clear, right? It's just, of course, addition is continuous. So F inverse of G of A is this. That's the definition. Okay? When X minus lambda is invertible. So, but this is open. Okay? This implies rho X contained in C is open. So sigma X is closed. So spectrum is compact. So spectrum is a compact subset of complex plane, and we want to prove that spectrum is non-empty. Okay? So usually in MNC, you will prove because I mean that it's algebraically closed. C is algebraically closed because of that. I mean, in finite dimension, something is in the spectrum is equivalent to saying it's an eigenvalue and it will satisfy the characteristic equation. I mean, characteristic polynomial. It's the root of a characteristic polynomial, which exists in the because C is algebraically closed, and you will get that the spectrum is non-empty. So here we have to do something because we are in infinite dimension. So an invertibility, I mean, something in, I mean, it's not operator to start with. We are in C-star algebra, but even when they are operator, something is in the spectrum doesn't mean it's an eigenvalue. So we want to prove that spectrum is non-empty. Okay? Okay. So for that, I define what is called a resolvent function. Okay? X in A. Okay. Then Rx is a function from the resolvent. This is the resolvent complement of spectrum to A, which is just you take lambda to X minus lambda. So Rx of lambda is X minus lambda. Then we have the following proposition, following properties. Limit mod lambda goes to infinity, norm of Rx lambda equal to 0 to, this is what is called resolvent equation. It says that Rx lambda, X is fixed, okay, Rx mu equal to lambda minus mu into Rx lambda and Rx mu. Third condition is the resolvent is what is called weakly analytic. Weak means it's analytic with respect to the weak topology. So what it means is the following. If phi is a linear functional, continuous linear functional, then lambda going to phi of Rx lambda is analytic. It's an analytic function. Yes, a complex, it's a function defined on subset of complex plane and the resolvent. So it's an analytic one. To prove when we want to consider, see, all those, if lambda is in resolvent, then this may not satisfy. But for lambda large, I mean, we want to consider, first we want to prove this, for that lambda going to infinity. So after some time, lambda will be greater than norm x, okay? So for mod lambda greater than norm x, okay? We have x minus lambda inverse equal to 1 minus 0 to infinity x power n by lambda n plus 1, which we did this calculation. And this is what is Rx lambda is. Now you calculate the norm of Rx lambda. Which is less than or equal to norm of the summation. 1 by lambda norm x power n by lambda power n. So this is equal to 1 by mod lambda times v 1 minus 1 by. Okay. This will go to 0, that will become 1. The same calculation we have, just geometric series, and we complete some. So 1 is clear, 2 is also clear. 2 we want to compute this lambda minus mu Rx lambda, we write it like this. It's scalar, of course, we can write it like Rx lambda, lambda minus mu into Rx mu. Okay. Now this is equal to Rx lambda into x minus mu x minus lambda. Rx mu. This is just x minus lambda inverse. If you take it, and this is x minus lambda inverse, and you take Rx mu inside, so this will just give Rx. It will cancel one of them, Rx lambda minus Rx mu. If you apply this, this will go away, and you will get Rx mu. If you apply this, I mean, if you apply here, you will get Rx lambda. So that's also clear. And the third one, phi is in A star. Now we want to prove that lambda going to Rx lambda. This is analytic, the phi of Rx lambda. Okay. We want to prove that this function, resolvent function, is weakly analytic, which means precisely this. So we want to prove that this is analytic. So we have to prove its complex functions. I mean, from complex plane to complex plane. This takes values in complex plane. So we have to prove it's differentiable. That's all. Okay. So to prove that, we consider that Rx lambda minus Rx mu, phi of this, phi of Rx mu, okay, divided by lambda minus mu, which we know equal to phi of Rx lambda times Rx mu. So which goes to, as lambda goes to mu, this whole thing will go to P of Rx lambda square. Limit exists. So it is differentiable. So it's analytic. Okay. That's all. You compute the limit direct. So you have done courses in complex analysis, no? So now let's prove the proposition. Sigma x is not non-empty. Proof. Suppose empty. Equal to empty. Then we have proved that this resolvent function is weakly analytic on the resolvent. Okay. Then this means that resolvent set is C. Okay. This implies lambda going to P, I mean P of Rx lambda is an entire function for all P in A star. It's analytic on the whole complex plane. Okay. And of course, it's bounded on bounded regions because it's analytic, in particular, it's continuous. So the problem will be only at infinity, but P Rx lambda goes to 0 as mod lambda goes to infinity. So this is bounded. This implies P Rx lambda is bounded. Okay. You know Liouville's theorem, and bounded entire functions are unbounded unless it's constant. So theorem implies P of Rx lambda is constant, but the limit at infinity is 0, so it has to be 0. Okay. Constant, and P of Rx lambda equals 0 for all phi in A star. Okay. And you know that, Hahn-Banach theorem. Hahn-Banach theorem says that as a consequence of Hahn-Banach theorem is phi is, the linear functional separates points of a Banach space. If you have, what is Hahn-Banach theorem says? Any linear function defined on subspace can be extended. Okay. So this will imply that there exists a phi for all x in, to separate points, you have to separate x and 0. Okay, because it's linear functional, so you can separate any. So given any x, you have to find a linear functional where phi of x is not equal to 0. Okay. For any Banach space x p, there exists a phi such that phi of x equal to norm x. You can find the phi of x equal to norm x. Okay. This is how you embed x into the dual of the dual. And x will, if you have a x in x, then you can embed this x as a linear function on x star. You will use this. Okay. So how do you do that? You take this lambda x. Okay. For a 6H, lambda in C. This is a one-dimensional subspace. Okay. Here you can define a linear functional at, this is just defined, the linear function on one-dimensional subspace is given by one scalar. You take that scalar to be norm x. Okay. So you can define phi naught of x is equal to norm x and extend it on this one-dimensional subspace. By Hahn-Banach theorem, you can extend to the whole space. So you get a norm phi equal to this. You get a linear for any given x. This is fixed x for a arbitrary x, for x in x. There exists a linear functional phi such that phi of x equal to norm x. So phi of x is not equal to 0. That's what it means. This is a consequence of Hahn-Banach theorem. We can call this as Hahn-Banach. Okay. So by Hahn-Banach theorem, phi separates points of any Banach space. So phi of Rx lambda equal to 0 for all phi implies that Rx lambda should be equal to 0. Hmm? Phi of x is this phi will have norm x. Once you extend, you can extend with the same norm. That's what Hahn-Banach theorem says. If you have a subspace, you have a linear functional defined on the subspace with some norm. I mean, it says something more. Hahn-Banach theorem something more about Minkowski functional and all that. Okay? By special cases, for a complex Banach space, if you have a subspace where you have a linear functional and it has some norm, say norm phi, then you can extend to a whole space with the same norm. It does, I mean, it doesn't increase the norm. With the same norm, you can, it's a bounded linear function with the same norm. It's a special case of this norm itself is a Minkowski functional, and you can use that. Okay. So that is Hahn-Banach theorem. This is a consequence of Hahn-Banach. You can define it on the one-dimensional space. I mean, you consequence of Hahn-Banach theorem, you can separate a subspace and a point. You can have a linear functional which is 0 on the subspace and it takes the value norm x on the point. That's by quotienting it, you can do it. Okay, it's the same. It's a special case of this. If you have a closed subspace, if you have a closed subspace, and if you have a point which is not in that subspace, then you can separate the closed subspace and the point. Which is a special case of this. You have to take, if you have a subspace, then you can take x naught. Then that this becomes 0. I mean, this subspace becomes 0 in that quotient space. You can separate that. So this is all consequence of Hahn-Banach theorem. Okay? If you are attending Ghana 2, I think it will be done. Okay? So corollary of Hahn-Banach theorem says that you can separate a point, any 2 points. I mean, you can separate a point and 0. So if in particular, if phi of Rx lambda is 0 for all phi, then Rx lambda should be 0. But Rx lambda is invertible, this is not possible. Rx lambda, but Rx lambda is invertible. Okay. So this is the contradiction. It cannot be 0. So we assume that it is empty, and using Liouville's theorem, we got a contradiction. So it has to be, it cannot be empty. It's just, I mean, not the direct proof. Still, it's a proof. Okay. So, okay. I have 15 minutes more. Are you tired? I mean, because you have maybe attended classes. I can go some more time, no? 15 more minutes. Okay. So this is about the spectrum. Next, we want to prove something. I mean, we want to prove something called spectral mapping theorem. Okay. Spectral mapping theorem is something like if you have, see, Banach algebras, we have something called analytic functional calculus. Okay. For any analytic function, you can, if you have an operator T, if you have a x in a Banach space, Banach algebra, then x power n makes sense. So any polynomial, P is a polynomial, then you can talk about P of x. This is algebraic. Okay. If you have an analytic function defined on a neighborhood around the spectrum, I mean, which is defined on an open set which contains a spectrum, then you can, if you have an f which is an analytic function which is defined on an open set which contains a spectrum, then you can talk about f of x. I mean, this is for a Banach algebra. If you have a C-star algebra, if you have any continuous function, you can talk about f of x. Further, if you have a Banach phenomenon algebra for any measurable function, you can talk about f of x. Okay, this is what is called functional calculus. I mean, this is just this association of f going to f of x for a x is what is called a functional calculus. Okay, so that we want to do it for a Banach algebra now, which is very direct. If you have an analytic function, you can do that. So proposition F is analytic. I mean, of course, F is from C to C. I mean, it's not F is analytic. It's defined on the open set with radius of convergence. Analytic means that you can expand it as a power series. Okay, that's what we will consider. Okay, convergence R which is greater than norm x. Strictly greater than norm x. Okay, so the spectrum will be contained in the open ball. I mean, closed ball with norm x. Okay, we have sigma x is contained in closed ball B of 0 norm x. I mean, it's analytic around 0 in a, let's say, let me say this, analytic in B0R. I mean, the center is 0. Okay? I mean, the analytic around a point, we will say the point is 0. Analytic in B0R. Okay? Is okay actually. Okay? With radius of convergence R center this. Then we know that sigma x is contained here. Okay? That's a consequence we will use. Then, so if f of z, I mean, and f of z equal to this, f of z equal to summation n equal to 0 to infinity an z power n for z in B0R. Then f of for x in, see here this z is complex number, x is in A. Okay? F of x equal to summation n equal to 0 to infinity an x power n. Converges. So this makes sense. This is the converges in A, of course. That is just direct. There's nothing in there. That's because, okay. No, wait. R should be greater than norm x, right? So I should say that R is greater than B0R and R is greater than norm x. Then further, so this you can make sense. Sigma x, I mean, you have a lambda here, you take all those f of lambda. And this is just f of lambda, the lambda x and sigma. This is something contained in the complex plane. Okay? This is contained in sigma of this f of x. Here f of x is an operator. I mean, f is a function. This is a function here. So f of sigma of x, which is a subset of complex plane. Okay. And here for x, f of x is defined through this because it converges. Okay. And sigma of that f of x contains this. Okay. For C-star algebra, when you have a continuous function, these are equal. Okay. First, we will prove for polynomial functional calculus, then we will prove for continuous function. Okay. That's the next class. Okay. So this is true for a Banach algebra. To prove, of course, since since norm x is less than R, okay, summation an mod x power n converges and equal to 0 to infinity converges. So f of z, f of x equal to summation n equal to 0 to infinity an x power n is in A, converges. Okay. This is just direct. Okay. So for polynomial, it is algebraic, but for any analytic function, we can define it. Here we need topology. It converges. Okay. Now we want to prove the second one is slightly, I mean, we have to do something to prove the second one. Okay. So now lambda is in C of sigma of x. Okay. Now we want to prove that f of, to prove this, we want to prove, what do you have to prove to prove that? So if lambda is in sigma of x, then f of lambda should be here. Okay. We want to prove f of, f of lambda is in sigma of f of x. That's what we want to do. Right? That's what we want to do. Okay. So to prove that, we have to consider f of lambda or f of x minus lambda, x of x minus f of lambda, right? Okay. Now that is equal to, and we want to prove that this is invertible, right? That's what we want to prove. So that is equal to summation n equal to 0 to infinity a n x minus lambda power n, right? Huh? Right? So sorry. You want to show the other way. Maybe I was wrong. Wait, sorry. You want to prove the other way, right? So once again, if we prove, now we want to prove the other way. Sorry. We want to prove the rho x. Sorry. That's what you'll follow. It was wrong. Right. So then what is the consequence? If lambda is in rho x, so this is what I will. Lambda is sigma n. No, that's fine. That's fine. I want to prove, let me write it and then get the right conclusion. Sigma x, then f of lambda is in sigma of f of x. This is what I want to prove. Okay, enough to prove if f of lambda, it was okay, right? F of lambda is in rho of f of x. Okay, then lambda is in rho of x. Okay? I proved this. That's what I'm proving. That's what I was trying to prove. Okay, this is okay. So I assume that f of lambda minus f of x is invertible. Okay. Then f of lambda minus f of x equal to summation n equal to 0 to infinity a n lambda power n minus x power n. Okay. You can write it as f of x minus f of lambda. This is equal to x minus lambda into summation n equal to 0 to infinity. You get this x power n minus 1 plus lambda x power n minus 2 up to lambda power n minus 1, right? This is what you will get. And n equal to 0, this doesn't make sense. So from n equal to 1. Okay? When n equal to first one will be, no, that will cancel, no? So it is from n equal to 1. The first one cancel. So this is from n equal to 1. So, okay, this is okay. So now this is something, you call it as Pn x lambda. Okay? This is an operator, of course. This is a finite sum. So this is an operator, finite sum. And norm of Pn x lambda. And you have a lambda and x. The power, total power is n. Okay, total power is n. So this is less than or equal to, and we have that norm x is less than r. So we choose a r which is between here. Choose r which is less than r and greater than 1. Okay. Right? This is less than r power n minus 1. So this implies norm of okay. So this implies f of x, let me write f of lambda equal to some x minus lambda times some c. I have to say that this converges. Where C is equal to summation n equal to 1 to infinity. An is there. There is an. An of Pn x lambda. And this has, I mean, no, this will be n times that. Sorry, this is n times Rn. See, summation n equal to 1 to infinity an of this Pn x lambda. If we take the norm, this is less than or equal to summation n equal to 1 to infinity an n times r power n minus 1. I mean, this is very similar to how you prove the derivative is also analytic. Same thing. This series converges. You can prove it. Okay. I mean, you have to. So this works. Okay. Mod a. This is less than infinity. Right. So this also converges. Okay. Without the thing. Yeah. Mod a. So this will converge. Okay? So you can call it C. Okay. So this is equal to C. So this implies f of x minus f of lambda equal to x minus lambda times C. So if this is invertible, okay, then so if f of x minus, I mean, this is f of x minus f of lambda inverse is some d, then what is the inverse of x minus lambda? That should be d times that, no? D times C. Yeah, dc. I mean, and notice that it commutes. What commutes? Everything commutes. I mean, this is something powers in xn. This commutation relation is see if some x yn, I mean yn converges to y, and xyn are commutative, then x and y also commute because the multiplication is continuous and all that. So this implies CD equal to x minus lambda. So we have proved. I mean, CD is equal to DC. Okay. I mean, it's up to n, it's just a polynomial, finite sum, and it's made up of this x and other things, so it will commute. So the limit will also commute. Okay. I have to prove something called spectral radius formula. Are you tired, or can I go? Whatever you say, stop, or it will take 10 minutes. What do you want? Okay, so then I will prove this. I mean, this will be a good point to stop. The proposition. So the proposition is, do I need anything else? No, I think this is enough. The proposition is, so you have to make a definition. X is in A, then R of x equal to supremum of mod lambda. Maybe it will take time, 15 minutes or something. Anyway, supremum of lambda is in sigma of x. Okay. Then this is R of, this is what is called spectral radius. Okay. Radius of x. Okay. It's just a supremum of, it's just the supremum of spectrum. Okay. The proposition is, this is what is called spectral radius formula. X is in A, then R of x equal to this limit of norm x power n 1 by n. See, usually x power n, norm of x power n is not equal to norm x power n. It will be less than that. Okay. So this limit exists and it is equal to this. That's what the theorem is. That's what the proposition is. It exists and it is equal to this. This is the spectral radius formula. I think it will not take much time. So proof. See this, if x is in row of x, so and p is in, first let's prove the one inequality. Okay. So the first one is if x is in A, okay, then norm x. We have proved this, right? We have proved this f of sigma of x is contained in sigma of f of x. Okay. So that implies that f of sigma of x, so sigma x power n, whatever it means, okay, this is contained in sigma of x power n. Okay. And we first know that r of x is smaller than norm x, which we have already seen. And we have proved that sigma x is bounded by something. So r of x is less than or equal to norm x for all x in A. Okay. Right? So this implies r of x power n is less than or equal to r of x power n. I mean, which is r of x power n, which is equal to, sorry, which is less than or equal to, this is less than or equal to norm x by whatever we have. So this implies r of x is less than or equal to lim n of xn power 1 by n. Okay. Now we will prove that this is greater than lim sup of that sequence. Okay. I mean, this is clear. No? The first we proved that sigma x is contained. I mean, anything lambda in sigma of x is less than norm x. We proved. So because of that supremum, we take the supremum. R of x is less than or equal to norm x. So from that, we've proved this analytic functional calculus, the property of the analytics, not precisely the spectral mapping theorem, some one way of that. Okay. Because of that, this is true. Okay. So we get this. Now we want to prove the other. Okay. Now let lambda is in row of x, which is not in the spectrum. Okay. Then we know that Rx lambda to prove. I don't, let me see. Rx lambda equal to x minus lambda inverse. Let me take a phi. Phi is in A star. Okay. Then phi of Rx lambda, which we have proved that this is analytic. Okay. And this is equal to summation x power n by lambda n plus 1, n equal to 0 to infinity, if lambda mod lambda is greater than norm x. This is what is called, this is a complex valued function. Phi of Rx lambda is complex valued function. This is what is called a Laurent series in the complement of the open ball, closed ball of radius norm x around 0. Okay. Laurent series, the coefficients, these are the coefficients. Coefficients are no, phi of x, sorry, phi of xn. This is the number, no, phi of xn. Phi of xn lambda power n plus. You know what is Laurent series? So this is just the coefficient of, I mean, where the one is an annular region, one annular is the interior disk is a circle is norm x, the other one is infinity. Okay. So this is the Laurent series of that. The coefficients are given by the Cauchy integration formula. Okay, they are fixed. So this will be valid for throughout the sigma x complement. Okay. I mean, with the complement of Rx, the open ball or if you don't like, and we know that phi of Rx lambda goes to 0 as mod lambda goes at infinity. It is 0 as mod lambda goes to infinity. Okay. At infinity, it is 0. So you can define analytic function. So you can define, for example, g of z equal to f whatever that phi of Rx lambda inverse. Okay, for in this B of 0 norm x, right? Norm x, 0, sorry, 1 by norm x. 1 by, what is it? Is it right? No, in the interval 0 norm x, right? The closed ball, even in the closed, you can define it. This is analytic, and z of 0 is 0. Rx, sorry, Rx, yeah, lambda inverse, correct. Okay, this is analytic. So the coefficients are fixed. So it will be, the same thing will be true for, I mean, in particular, I just want to say that this equation is valid in the bigger region, in rho of x itself. Okay, because the Lorentz series is determined by the coefficient, which are actually given by the Cauchy integration formula. I mean, you know that Cauchy integration formula. Each coefficient is given by some z power. I mean, z power. I mean, z power. The center is 0, so z power n or something. Okay. So because of that, this Lorentz series is valid here. So in particular, I mean, all I need is in particular this converges to 0. This an converges to 0. Okay, phi of xn by phi of xn goes to 0, right? Phi of xn by lambda power n plus 1 goes to 0. In particular, they are bounded for lambda in rho of x for all norms. That's what I want to do. In particular, phi of xn by lambda n plus 1. So this is less than or equal to k times lambda n plus 1. Okay, this is true. I'm just saying this is true. Phi of xn, right? X power n is less than or equal to k times lambda power n plus 1. This is true. Okay, so okay, so now see here we are using the uniform boundedness principle in so this is something I said about Hahn-Banach theorem. The Hahn-Banach theorem says that for every, I mean, I wrote a consequence of Hahn-Banach theorem. This is another, I mean, see, here phi is a fixed element. I mean, no, phi x is a fixed element. See, if Hahn-Banach theorem says the following: if x is a Banach space, okay, and if you have x in x, okay, then you can define a phi x from x star to c, where phi x, maybe x hat, let me say x hat from x star to c, where x hat acting on any phi is phi of x, evaluation function. So here x is fixed, phi is varying. Okay, so this x hat will be in x star by Hahn-Banach theorem, and you can see that norm of phi is less than or equal to x hat is less than or equal to norm x. By Hahn-Banach theorem, the norm will be the version of Hahn-Banach theorem I just said. The norm will be attained, and now Hahn-Banach theorem will imply that norm x hat will be equal to norm x. Okay, so this x acts as linear functional on phi. Now I use the uniform boundedness for those x hat. Okay. I say that phi of xn is less than or equal to this. Here phi is varying. This is for all phi. Okay, for all phi in A star. Okay, this implies norm of xn is less than or equal to k times mod lambda of n plus 1. Okay, so now we can see that you can take the but lambda is coming from the rho of x, no? Yeah. Now lambda is coming from rho of x. So this will imply that you can take the nth power. There is a, I mean, this is okay, no? You can take lambda n. This is okay. Okay, and this implies that all I want to say is the following: mod lambda power k by 1 by n is greater than or equal to norm xn power 1 by n. Okay. So this goes to 1. So this implies mod lambda is greater than or equal to lim sup of xn power 1 by n. Okay. We have proved that. No, we have proved that r of x is less than or equal to this. This will imply, does this imply that, and we have proved that something is in the, which is also r. As lambda goes to, yeah, I mean, you can take lambda as lambda goes to r of x. This is good. So this, yeah, good. This is just the, you can take it the infinite, no? So this implies r of x is greater than or equal to lim sup. Yeah, good. Because I took the lambda from the resolvent, no? So I was a bit confused. Yeah. So you can take as lambda goes to Rx. Okay. Since it's compact set, so I mean it's a compact, you are using the compactness of sigma. Okay. So R of x is greater than this. So this implies R of x equal to lim. So the limit exists and it is equal to x power. Okay. And for a normal element, when you have C-star algebra, it will be equal. We'll prove. Ulo. The video has gone. And then